system is large enough. And you can put this to this hole or the other hole, so the total number of four states. And that's the fourfold degeneracy. Okay? So now I can recall this phase diagram, and I've now proven that there are in fact two phases which can be distinguished, which require a phase transition separating them. One has short-range order. They both have short-range order. And to really distinguish them requires either putting them on a torus or looking for these excitations that only exist, that cannot be created by any local operators. So it's quite subtle, but they can be distinguished. And also for the experts, let me say that this is the state with topological order. It is the same topological order in the toric code, and also in this U1 cross U1 Chern-Simons theory.
So if the U1 cross U1 has to be mixed.
Yes, so it preserves time reversal, so it has to have two fields. It doesn't break time reversal. Okay. Yes?
So in order to get the thetas are not, when you don't live on a circle, but they're just the two variables, then the topological and the long-range order are connected. This solves out by patching and cancer, right?
Yeah.
So like at what point, then you can imagine the thetas living on many.
Well, I mean,
At what point does the second equation between
well, if you can define a gauge invariant order parameter that breaks a global symmetry. So if the sigmas have, so you have, I think what you're saying is you have Ising matter fields, there's no broken symmetry. That's true because the square of sigma is 1, so there is no, but if you had even a 4-state clock model, then the square of it would be gauge invariant and have a Z2 symmetry. So then there would be a phase transition. So the only case that you don't have a phase transition is one you mentioned. The moment you have any gauge invariant order parameter. So psi, remember, was gauge invariant. And there was a global symmetry. So, other questions? Yeah, Shiraz walked in just in time to see this. I just put it up for you. Yeah, sorry.
So I can ask it again at the end, but in case one there's a duality transformation.
Yes.
And turn the vortices into particles.
Correct, right.
And when you think of it as a situation where you have two kinds of particles with charge 1 and 2.
Yes.
The charge 2 condenses, but not the charge 1.
Exactly, yes. But they're coupled to a gauge field there. It's a gauge theory with two charge. Yes, you can do it that way too. Okay, just for sure. That's the Hamiltonian. Has three phases. The familiar phases with what's the trivial phase and the Higgs phase, the long-range ordered phase, and a topological phase, which has the order of the toric code or this U1 cross U1 Chern-Simons theory. Okay, so that's been then a review of a toy model where I've introduced the idea of topological order as associated with I mean, the qualitative idea was just we're going to get rid of these defects, some defect, and what I've shown is that when you try to do that, you end up with, to make it more precise, you have to talk about things like degeneracy on a torus, at least if you have a gap, or the existence of new types of particles that are totally stable and cannot be destroyed by any local operator. All right, so now let me get to the Hubbard model, something more realistic, so the experimentalists can hopefully pay attention now. No, hopefully if they were still awake. All right, so this is the Hubbard model. It's electrons hopping on a lattice with some local repulsion U, and at some density. Okay. So first, let's just treat it in the simplest possible way. Now, it turns out, through some fairly simple arguments, you can see that this U term prefers a broken symmetry where the electrons are antiferromagnetic, that one sublattice is up and one sublattice is down. So let me just take that very simple case take the electrons, be up and down, and form that be my order parameter. So then I could just do some mean field theory, Hartree-Fock theory of this term, and work out some qualitative mean field phase diagram, and this is what it'll end up looking like. So this is my order parameter. I just take that and factorize the Hubbard model, and as a function of U over T for some generic density and generic filling factor, generic hopping matrix elements, this is the kind of thing I'll get. There'll be the phase with no broken symmetry, in which case you can just think of the electrons as being basically free, and they occupy some states inside a Fermi surface. And now this Fermi surface is conventionally in the literature referred to as large because of what's to come. And it obeys what's called the Luttinger theorem, that the volume enclosed by the Fermi surface is equal to the density of particles. On the other hand, in the other phase, there's a broken symmetry. The spins form this staggered arrangement. And then you can work out, as I'll indicate in the next transparency, what the Fermi surfaces do. And the jargon in the condensed matter literature is the Fermi surface reconstructs into various pocket Fermi surfaces. And now you can see in this picture that the volume enclosed by these pockets is much smaller than the volume here. But that's not a cause for alarm, because the precise statement is that, let's just do it per spin. The precise statement of Luttinger theorem is that the volume enclosed by the Fermi surface is equal to the number of particles mod 1. It's mod 1 because you can always take a filled band per spin. That won't get, just put in some very low energy band, you can put 1 electron per spin. That's not going to change the low energy behavior at the Fermi level. So you can always take out an integer number of electrons. And what's happened here is that because of the antiferromagnetic order, the unit cell has doubled. So in this doubled unit cell, per spin, there's 1 electron. So in fact, you can take out 1 per unit cell. That's the statement. And that's why this obeys Luttinger theorem. Because somehow the broken symmetry then allows you to have much smaller Fermi surfaces. Okay? That's a review of solid state physics 101. So my question is, can I violate the Luttinger theorem? Can I get a metal where I don't have this big, large Fermi surface, but have a Fermi surface that looks sort of like this? Can I get it without actually breaking a symmetry? And there's various reasons from experiments that this would be a nice thing to have, because something like this seems to be happening. I'll show some of the pictures later on if there's time. It looks like there isn't. Can I do this and not break a symmetry? Well, so there were arguments by Oshikawa first showing that this Luttinger theorem had a topological character, and then a paper by Senthil, myself, and Vojta showing that yes, you can do this, but you must have topological order. So in fact, you don't actually need broken symmetry. Topological order is enough. I want to show you a very simple argument where you can actually see how this happens. And that argument, in keeping the theme of my talk, will have to do with suppression of defects. It's all about defects. That's another reason why I think this definition of suppression of defects is a nice way of thinking about what is topological order. Okay, so everyone clear as to what the question is? That's the question. And the answer is yes, but I'll give you the answer, show you how explicitly. Okay, so it is a very simple, there are many ways of doing it, but let me show you how, in a very simple way, in a very simple model, how this works. So let's start with the Hubbard model. So these were the usual terms, the two-body terms. And then there was some interaction. And the interaction, I do a Hubbard Stroudnovich, and I decouple it into the antiferromagnetic order times the local spin density. In fact, this is exact. You can just integrate out phi and get back the U interaction I had before. So, but forget that. I mean, this is just telling you when you have a broken symmetry, that looks like a potential acting on the spin density of the electrons. That's all. It's a plus potential for the spin up electrons, and it's a negative potential for the other ones. Okay. And it's oscillating at pi pi. That's what this eta I is. Okay. So now when phi is constant, well then you have to, this is just still a quadratic term. You can re-diagonalize the Hamiltonian, and you get these small pockets, as I've already indicated. All right. Now I want to do the following. I want to imagine a situation where phi is large locally, there's antiferromagnetism locally, but it's changing orientation as you go from point to point. I'm going to allow some fluctuations. And as you'll see, what I'm going to need is to allow lots of fluctuations. If they're arbitrary fluctuations, then it's as if phi isn't there. But if they're of the right type, you can get topological order and some added benefits. Okay, so the way I'm going to do that is imagine phi is rotating from point to point. So I just go into a rotating reference frame. So this is the original electrons. I'm going to write them in terms of new fermions called psi, which are related to C by some SU2 rotation. And when I rotate the fermions, I should also rotate phi by the same SU2 rotation R. And that's since phi is a vector, this happens in this way. And this new field H is the antiferromagnetic order in the rotating reference frame. And I'm going to call this a Higgs field. So the Higgs field is, basically you have some antiferromagnetic order. I go to some other frame of reference, and I ultimately want to go to a frame of reference where and in the new frame of reference, the antiferromagnetic order is constant. Or the Higgs field is constant. Okay? So the Higgs field being constant doesn't mean I have long-range antiferromagnetism, because there's still a frame of reference that's changing from point to point. Okay. Now, why did I call it a Higgs field? Well, this decomposition by very construction is an SU2 gauge theory, because there's no unique decomposition of C in this way. I can always put a factor of V dagger in between. And so these new fermions carry SU2 gauge charges. The Higgs field has SU2 adjoint charges, and this R also has an SU2 gauge charge. And this has nothing to do with the spin rotation symmetry. I could do this no matter what the Hamiltonian for these C's. It doesn't have to have spin rotation invariance at all. It's really, as we'll see, a key characteristic of a phase which has topological order. It's nothing to do with global symmetries.
So the Higgs is itself a doublet.
It's a triplet.
It's a triplet.
It's another boson, which is a doublet under SU2. It also has global SU2 spin charges, because the up-down is the left index of R. So it's a kind of a subtle thing. So all right. If you had long-range order, the R will have a Goldstone mode. But you need R to condense to get long-range order. That would be the Higgs phase of the R. So there's two bosons. There's the Higgs boson, which is a adjoint, and there's the R boson, which is like a matter field, which is a fundamental of SU2. Okay. I'd be happy to discuss. I don't want to use all this fancy gauge theory language, because the basic point is actually very simple. So, like I said, the reason we want to go to a rotating reference frame, we want to imagine a situation where the antiferromagnetic order is replaced, where the Higgs field is constant. And so in this rotating reference frame, we'll have an effective Hamiltonian where these new fermion psi's are moving around. They'll be coupled to some gauge field, which I'm assuming is weakly fluctuating. I haven't shown it. And then it will also experience this Higgs potential, or this is a Yukawa term. So the Yukawa term will act on these new fermions. Now, particle physicists know that in the Higgs phase, the Yukawa term gives the fermions a mass. So in condensed matter physics, in the Higgs phase, the Yukawa term reconstructs the Fermi surface from large to small. Basically, it just gaps out some portions of the Fermi surface. You can't give all the fermions a mass, you only give some of them a mass. That's just a question of the nature of this matrix, that's all. All right, so then we conclude that if we can succeed to find a frame of reference in which the Higgs field is constant, then I'm done. I haven't broken any symmetry because the antiferromagnetic order is fluctuating. But in this new frame of reference, these fermions psi have a mass, or in other words, the fermions psi have small Fermi surfaces. So this almost seems too easy that what happened to Leibniz's theorem? How can I get away with this? Okay. So the key is defects. So now here I'm simplifying. Let's imagine I'm talking about only XY spins. And suppose in the antiferromagnetic order I had a vortex. And now I have to find a field R which is going to make this a constant. All right, if I take a pick R and I go around the vortex, it'll come back to -1 for an n-fold vortex, -1 to the nr. So this means if R is not single valued, it means the field psi is not single valued, at least if you take the lowest energy state. And therefore, this tells me that I can only get away with having a constant H if these vortices, odd vortices, don't exist, which is what I talked about in the first part of my talk. Therefore, I can get a metal with small Fermi surfaces, provided that metal, the antiferromagnetic order in that metal, has no odd vortices. But the whole point of the first part of my talk was to show, well, that